Hello and welcome to the lecture on the buoyant force. Okay, so let's discuss what the buoyant force is and why we're seeing it in a chapter on fluids. Okay? All right, so what is the buoyant force? Well, we're looking at a picture of it over here. All right, so apparently it has something to do with the forces that are exerted on an object when it's in a fluid. Maybe floating in the fluid, maybe sinking, but obviously there's some density here, the density of the fluid. So it's a fluid force. All right? Well, a good description for it is the fluid equivalent to the normal force. You set something on a table, the table pushes back. Well, if you put something in water, the water pushes back. But not quite in the same way, right? Because things sink into the water. So since the water is movable, deformable, it's a fluid, the force behaves a little bit differently. All right? It is or can be thought of as a reaction force exerted on an object by a fluid. Okay? So you push on the fluid pushes back due to Newton's third law. All right, so it's a reaction force from the fluid on an object. Okay? And it's equal to the weight of the fluid displaced. So for practical purposes, that's an idea you'll come back to a lot. You say, oh, okay, well, the magnitude of the fluid of the buoyant force is just the weight of the water, usually, that was pushed out of the way. Okay? All right? And it is created, a little bit more of kind of where it's coming from, by the imbalance of pressure and thus the force acting on the top and the bottom of the object in a fluid. Okay? Because if we think about it, so the imbalance in pressure means an imbalance in force. Because the bottom of any object, consider an object here, the bottom of the object is at some depth h2. The top is at some depth h1. All right? And that means due to hydrostatic pressure that says P equals rho GH, well, there's going to be greater pressure at the bottom than at the top. Okay? And that means when the areas are equal, there's greater force. And even when the areas aren't equal, there's always a net upward force due to the fluid, just because of that depth-dependent pressure. All right? So very much comes from pressure. You can't get the buoyant force without pressure. And of course, pressure is related to force because pressure is just force per area. Okay? So that's the idea. That's where it comes from. But again, in practical purposes, it's always just equal to the weight of the water that's displaced. And weight is a force, right? That would be the mass of the water displaced times gravity, and then that's your magnitude of your buoyant force. Okay? All right, so let's see it in equation form. All right, here it is. Zoom in a bit on it. This is F sub B, B for buoyant. That is the buoyant force, right? It's a normal force. It's measured in newtons. Okay, and this is what it's equal to. Here's the formula for it. It is the density of the surrounding fluid, water, air usually, and the volume of the fluid displaced, and then just times gravity, 9.8 meters per second squared. Okay? So for objects that are sinking or that are fully submerged, like in our example diagram here, the volume of fluid displaced would be equal to the volume of the object. Because if you know the volume of the object, you know exactly how much fluid is displaced. And if you know the density, like the density of water, 1,000 kilograms per cubic meter, well, there you go. You got your buoyant force, your magnitude. And you know it points up because it's a reaction force. A reaction force that's driven by, well, things pushing down on it, okay, which has to be driven by gravity, so it always pushes up. All right, so there you go. You're done. Floating is a bit more complicated. Floating is just the volume that's displaced, and that depends on how much of the object is floating above the water line, above the surface of the fluid. Obviously very light things like styrofoam, like most of them float above the water. Heavy things can float with just a little bit sticking above the water. So in that case, the volume displaced has, it's, how do you find it? Well, it turns out that it's just equal to the ratio of the densities, the ratio, specifically the density of the object over the density of the fluid, times the volume of the object. And how do we know that? Well, we know that from a simple force diagram, right? Because if I think of a case where something's floating, well, then F net has to equal 0, right? Floating, by definition, is equilibrium. Because you can be sinking and have an acceleration, but you can't be floating and have an acceleration. Okay, so if that's the case, then your two forces would be your buoyant force pointing up and your gravitational force pointing down, and they'd be equal to 0, right? Okay, well, the buoyant force is still rho F V F G, and then the gravitational force is just mass of the object times g, but the mass of the object is, after all, the density of the object times the volume of the object times g equals 0. Well, now look at it. Now we can solve for Vf. Think about this. The g's cancel, and I just solve for the volume displaced, and it's always just going to be equal to the ratios of the densities times the volume of the object. There you go. Quick derivation. And you can always do that and rederive it for yourself, think about where it comes from, or you're welcome to memorize this and just say that the volume displaced for a floating object is just the ratio of the densities times the volume of the object. Okay? And you can always remember that the volume of the object is on top of the ratio, because otherwise it wouldn't be floating. Because if the object's denser than the fluid, then it sinks every time. All right, let's look at our examples. I'm going to get right into them. Because there's not a lot of concepts here, it's just that one concept, the buoyant force, and then we put it to practice. Okay? All right, so 3 types. Type 1, problems involving the buoyant force on objects that are completely submerged in a fluid and at rest. Okay? Problems that involve the buoyant force on objects that are completely submerged in a fluid and accelerating. Okay, so kind of subtle difference there. One of them we're going to set the net force equal to 0. The other one we'll set it equal to ma. All right, great. And m would be the mass of the object. Type 3, problems that involve the buoyant force on objects that are partially submerged in a fluid and floating at rest. All right, there we go. And we could technically have, I guess, type 4, I don't have it, where you could have something partially submerged, like floating, but you could have it, or you could have something partially submerged but not floating, because you could have an extra force like tension or something, right? So you could have the idea that you're holding something and supporting it, it would otherwise sink, and but you submerge like half of it, right? But we won't do those in the basic problems, and I don't have a challenge problem plan like that, so we shouldn't be seeing it. Okay, so example 1. A piece of metal is hung from a vertical spring scale in air and a weight of 12 newtons is recorded. The metal is then fully submerged in water with a density of 1,000 kilograms per cubic meter, and the same vertical spring scale now reads 10.5. It reads less. That makes sense. Things should weigh less when they're submerged in water, because now there's something else pushing up on them, counteracting some of the gravity, the buoyant force, right? So both weights are taken when the object is at rest, and the air is assumed to create 0 buoyant force, because it is, it's 1,000 times less, right? Remember that the density of air is 1,000th of the density of water, so it's a fair assumption. And now the question is, what is the density of the object? Because this is pretty cool. We could always take these 2 readings, a reading in air and a reading in water, with a known density of the water, and there we go. We know the density of the object. Cool. Here's the picture. Here's the measurement in air. In the measurement in air, there's just the tension force acting on the object and the gravity acting on the object. And the fact that 2 tension forces are shown here is just the idea that the spring here is assumed to be massless, so it transmits the force completely, and so then the actual force measured on the measurement part of the scale is just the same tension, right? Just to call attention to that idea in case you're rusty on it. Okay, and then here I just wrote all the forces acting on the object when it's on the water. The idea there is we have a different tension force, Ft prime, less, right, 10.5, and now we have a second upward force, the buoyant force. All right, so you probably maybe guess where it's going, but let's go through the steps. So the spring scale in air reads Ft, and Ft just equals Fg, right? Because it's at rest after all. All right, so that means that 12 newtons equals mg, which means that the mass is 1.22 kilograms. Okay, great. All right, and that's just to find the mass. Okay, and so in the water case, now we have the net force in the y direction, defined as up for positive y. And we have the buoyant force, the new tension force minus gravity equals 0. Okay. And we're going to go ahead and solve for the buoyant force, which is just going to be the difference between mg and the new tension force. All right, and then we'll put in the buoyant force in the form of the density of the fluid, the volume of the metal. Okay, the volume of the metal, that's important because it's fully submerged, right? The metal's the object after all. G minus Fg minus Ft. Okay, so then we can solve for the volume of the metal. See where we're going with this? Okay. And once we plug in our numbers, plug in the mass that we're given, plug in gravity over here, plug in our Ft prime, our tension force when it's in the water, and then density times gravity. Okay? So we get a volume of 1.5 times 10 to the negative 4 cubic meters. Small because volumes tend to be small, right? Remember, there are, after all, 1 million cubic centimeters in a cubic meter. So, give you some perspective here. Okay. Well, look, think about it. We've got a mass and we've got a volume. That means we can find density. Right? So in the density of the metal, and there's different ways to go about doing this, but I think it's a very intuitive way. So algebraically, there's different approaches. And so here we have the idea that the density of the metal is just our 2 values we found, mass over volume. And there we go, plug in our numbers, and we go 8,130 kilograms per cubic meter. What would the specific gravity be? 8.13, right? Because it's 8.13 times density than water. All right, cool. Good use of the buoyant force, right? Find the density of an unknown substance. Okay? All right, now let's consider something that's accelerating. A helium balloon with a density of helium, which is 0.09 grams per liter, has a spherical shape and a radius of 10.8 meters. If this balloon is released in perfectly still air with a density of 1 kilogram per cubic meter, what will be the initial acceleration of vertical ascent of the balloon? All right, so one thing we want to do here is we want to convert over our density. So let's think about this, right? So I've given the density of helium in grams per liter. Okay, so if I have my density and it's 0.09 grams per liter, all right, and then I've got, I want to convert that to kilograms per cubic meter. All right, so then I'm going to then say that I'm going to have 10 to the negative 3 kilograms per gram. All right, so let's see. Okay, and so then, we'll convert over. We've got, so then how many liters per cubic meter? Okay, well that one is 1,000. All right, so then we have our 1,000 per, so then we'll have our cubic meter. So I have 1 liter up here and then 1,000, or actually no, so I have my 10 to the negative 3, oh, that over here, 10 to the negative 3, and then this is going to be cubic meters, okay, we'll cross that out, and then there's liters up top, okay? So there we have it. And if you see, what happens is it cancels out. Cool, right? And so then we actually find the grams cancel and the liters cancel, and then so when we get kilograms per cubic meter, it's exactly the same. All right, so a gram per liter measurement is the same as a kilogram per cubic meter measurement. And I bring that up because I didn't mention that last time when I talked about density, because I talked about how a centimeter, or rather a gram per cubic centimeter, is not the same. It's always going to be 1,000 times less. So 1 gram per cubic centimeter is equal to 10 to the negative 3 kilograms per cubic meter. All right, but with grams per liter and kilograms per cubic meter, it's the same, exactly the same, which is pretty neat, okay? And you just always have to remember is that there's 1,000 liters per cubic meter, okay? All right, so with that out of the way, we're good to go. And yeah, actually, you can kind of already see that it's going to cancel out because we got a factor of 1,000 here, all right? I said we're good to go, but I just wanted to point out they're each 1,000, right? There's 1,000 liters per cubic meter and there's 1,000 grams per kilogram, so that's kind of the giveaway that it's going to be the same. All right, so then moving on, let's draw the picture. All right, so there's the buoyant force and gravity. That's it, just the two forces acting on the balloon. Positive wise to find this out. All right, so our net force is going to be buoyant force minus gravitational force, not equals 0, but equals ma, because the object should definitely accelerate. It should accelerate because the buoyant force is definitely going to be bigger than the gravitational force, okay? And that's because the helium is much lighter, and it is quite a bit lighter, right? It's about 10 times lighter than air, right? Really significant difference. And then we're going to replace both the buoyant force and the gravitational force with forms that include density. So the buoyant force then is going to be the density of the fluid times gravity times the volume of the object because it's completely submerged. The gravitational force is going to be the density of the object times the volume of the object times gravity. You'll be like, wait, isn't it just mg? Well, yeah, because this is m, right? Density times volume is m, right? But we're just writing in a way where then we can simplify the expression. And then over here we have m again, so that's just density times volume yet again, object, and then a. Okay, well look, the volume of the object cancels out. My goodness. It's independent. So it doesn't matter how big your balloon is. It only matters what its density is, okay? Now here's the thing, is that in reality, when you have a balloon, the fabric that it's made out of, or the material, is going to be a different density. As you make it bigger, then the surface area to volume ratio changes, okay? So there actually is a functional dependence that would affect the size. But if we're assuming that somehow you have some like infinitely thin membrane that's holding the helium in, then truly the volume would cancel out. Okay, so that means the acceleration ends up just being gravity times this ratio of densities, which is the difference between air, in this case the fluid, minus the density of the object divided by the density of the object. So we plug in our numbers, gravity, and then 1 minus 0.09 divided by 0.09, and we get 99. Okay, so you might be like, wait, 99, so that's accelerating at 10 times the rate of gravity? Well, that's too fast. Well, here's the thing. As soon as this thing starts moving, it's going to start experiencing a drag force. Drag is proportional to velocity. And so that means after its first moment of acceleration, it's going to have an initially large velocity. That means drag is immediately going to slow it down. And this is a very drag-induced object here. It's going to create a lot of drag, right? A big sphere. And so the idea is certainly this would be the instantaneous initial acceleration, but it wouldn't be sustained. Okay? All right. So moving on, example 3. The helium balloon's back. But this time we've attached a basket to it, okay? So helium balloon, we have the density of helium. 0.09 grams per liter, has a spherical shape and a radius of 10.8 meters. If this balloon is floating in perfectly still air with a density of air of 1 kilogram per cubic meter, what is the heaviest loaded basket such a helium balloon could keep suspended above the ground at rest? All right, ignore the volume of the basket. Now, the reason that we're ignoring the volume of the basket is because it would create a buoyant force, okay? Depending on whatever its density is, right? We need to know either its volume or its density, considering that we're finding its mass. But whatever its density is, right, it would create a buoyant force. And then the thing is, then that buoyant force would change the problem. But think about it. Whatever it is, its volume is going to be much, much smaller than the volume of the balloon. So whatever buoyant force it's creating due to pushing on air is very, very negligible, especially considering that it's going to be much denser, okay? And so it makes sense to ignore it. It is an interesting complication to the problem, and it does significantly complicate the problem when we add it in. And it's good. It's a good complication, but it's just not one that we're going to do, okay? All right, so for once, we're going to keep it simple. All right, so here we have our upward, or the net force in y. Positive y is defined as upwards. All right, we got our buoyant force, gravitational force, 1 and 2. 1 and 2 because this is just the weight of the balloon, and then this is the weight of the basket, gravitational force 2. And definitely equal to 0 because it's at rest, all right? And, when the load is maximum, right? It's, at rest. All right, do the same sort of substitution, define the buoyant force, replace gravity of density times volume. Here we're actually going to leave the mass of the basket because we're not interested in its density. We actually just want to find m. So I'm going to leave it in the traditional mg form for Fg2, all right? Because m2 is the mass of the basket, a different subscript, right? And then we're just going to solve for the mass of the basket. And where does 4/3 pi business come from? From the volume of the balloon. Because this is the equation for the volume of a sphere, 4/3 pi times r squared. And we were given the radius, so we can just plug that in. All right? And we know everything else. So then we're just going to go ahead and solve for the mass of the basket. And we get 4,800 kilograms. Right? So a lot of weight, a couple cars, right? Large cars that this balloon could support. But it's also a huge balloon, right? It's like 60 feet across. That's a giant helium balloon. All right, cool. All right, moving on. Now this is an interesting concept question. All right, so let's go through the steps here. It's a good one. Okay, so a steel axe and an aluminum piston have the same apparent weight in water. And apparent weight would be like the example 1 where we had the spring scale, right? And we were talking about this. It'd be like if we weighed something in water, that's its apparent weight. We know it's on its true weight because we know the buoyant force is affecting it. That's what I mean by apparent weight. So these two different objects have the same apparent weight, right? When they're weighed in air. In this case, we'd never weigh them in, or rather, first of all, we weigh them in water, and they have the same apparent weight, okay? And I remind you that aluminum is less dense than steel, okay? Right? I think we know that, but aluminum is less dense than steel. Okay. So then, when they're weighed in air, which one is heavier? Or do they weigh the same? So this is so interesting, because it's like we only know half the information. We only know what their apparent weights are in water, and we know which one is denser. So what does that tell us? Which one must weigh more in the air? I want you to have a guess, right? If you're watching this video, listening to this video, think to yourself, which one is it? Is it the less dense aluminum that would weigh more in air, or the denser steel that would weigh more in air? Okay, well, let's see. So we're going to set this up, right? Weight apparent, okay? And so then we have that the weight apparents are equal to each other. The weight apparent is going to be the buoyant force minus the gravitational force. So the buoyant force is the density of the water times gravity times the volume of the axe for the steel axe, and then times the mass of the axe times g. Okay, that's going to be equal to the volume of water times gravity times the volume of the piston times the mass of the piston, the aluminum piston, times g. Okay. Now we can say here that it's the volume of the piston and the volume of the axe because they are fully submerged. Okay, because they're both that's it. I guess we have to assume that, but they are fully submerged. And then g cancels out, right? And setting these two things equal to each other. So that's all we're doing is setting these two equations equal to each other. Okay. So and then I just cleaned it up a little bit. Still have them equal to each other. All right. So then we're going to go ahead and solve for the mass of the piston. If I solve for the mass of the piston, then I'm going to, I will have the density of, over here, let's see. Okay, so I'm solving for the mass of the piston would involve adding the piston to both sides because it's negative. So I'm going to add the piston to this side and then subtract these two terms over to this side, okay? And then when I do that, I factor out the density of the water. So then it'll be volume piston minus the volume of the axe, because remember I subtracted that term, okay? And then and then I also have this term, the mass of the axe, which I'm going to subtract from both sides, which is like adding it to the right-hand side. Okay, so that's where it all comes from. Okay, and then we know that the mass of the piston, which is equal to this expression, is going to be greater than the mass of the axe. Can you see that? Because it has to be. Look, because the idea is that, we have here that we have the mass of the axe plus something, okay? And you might be like, well, can you really say that? Are you sure it is? Because if that's the case, if the mass of the piston is greater than the mass of the axe, then we're done, right? Then we've answered the question of which one weighs more in the air, because in air, definitely whichever one's more mass is the one that's going to weigh more, clearly, right? But are we confident that this term is not negative? Because if this term is negative, then this does not mean that M piston is larger than M axe, mass of the axe, because adding a negative term would then make this side of the equation smaller than the mass of the piston, okay? So we have to then actually make sure that that the volumes match up, that the volume of the piston is in fact larger than the volume of the axe, all right? Well, so we can say that because let's see. If we go back to the original expression up here, but we rearrange things a bit differently, and we solve for the volume of the piston, look what we get, right? So this is just solving for this. So again, I'd add it to both sides to make it positive, and then I'd subtract everything over to this side, and then I'd divide both things I'd divide by the densities that's attached to the volume of the piston. I'd factor out the volume of the piston, because it's in both these terms. And I'd factor out the density of water and the density of aluminum, all right? And look what we have, okay? This tells me that the volume of the piston must be greater than the volume of the axe. Why? Well, because the density of aluminum is less than the density of steel, right? And so if we look here, right, we've got, right up top, we've got the density of water minus the density of aluminum, all right? So this is going to give us a negative term. And then over here, we're going to have the density of the water over the minus the density of steel, also a negative term. But which one is going to be bigger? Well, the bigger difference is going to be the one on top, all right? So we have, so essentially, when we have then that means that this term is always going to be, or I should say this coefficient here is always going to be greater than 1, which tells us the volume of the piston will always be greater than the volume of the axe, okay? And that makes sense because if you have two objects, and they both experience the same buoyant force, then the way, or I should say they both have the same apparent weight, the only way for that to happen is for the one that's less dense to be bigger, all right? So there we have it. And I told you, it's an interesting journey to see how, a fairly simple question, right? But the algebraic approach really does demand a lot of kind of considerations of inequalities and carefully thinking about what we know, all right? All right. So let's move on with a couple more examples to wrap this up. So a large boulder is being vertically moved off the side of a ship using a winch, all right, a winch cable. So in this case, it's a fully submerged object, but it's going to be accelerating. It's going to be accelerating because there's going to be tensions involved in this problem, right? So here's the system: buoyant force, tension force, gravitational force. Positive y defined as up, okay? So first of all, based on the density we're given, because we're given the density of the boulder, here called the rock, we're given it in 2.6 grams per cubic centimeter, right? We'll have to convert that over. It becomes 2,600 kilograms per cubic meter. And we're told it has a volume of 112 cubic meters. And so then we go ahead and find its mass, and it's got a mass of 291,000 kilograms, all right? Big boulder. Good, so good number to take note of. All right, so then move on with the problem. All right, sum of forces, I'm gonna zoom in a bit on this. All right, so, and you notice, right, these problems of buoyancy, they're all about sum of forces problems, right? It's just, something we're totally used to applying Newton's second law, but we're just doing it with a new force, all right? All right, so buoyant force, tension force pointing up, gravity pointing down, and an acceleration. And specifically in part A, we're asked if the tension is this particular value, then what is the direction and magnitude of the acceleration of the boulder? Because here's the thing, right? If this tension isn't great enough, then the boulder would still be sinking. If the tension is just right, then maybe the acceleration is 0. And if the tension is more than enough, then it would actually be accelerating up, right? So let's find out which of the cases that it is. All right, so in our net force, rewrite the buoyant force. Volume displaced is going to be the volume of the object, right? We'll make that substitution in a second. Tension force is just a number, so we'll just leave that. And then minus mg equals ma. All right, and then here I point out that the volume displaced is going to be equal to the volume of the boulder. All right, and then we're just going to solve for acceleration. We got the density of the fluid. We've got gravity. We already know v because it's 112 cubic meters. Ft is the number that we're given. We found m through a quick calculation. All right, so then we can just find acceleration, plug in our numbers, and we get a positive value. Okay, a positive value based on our coordinate system tells us that the acceleration must be up. So that means that this is more than enough tension to accelerate the boulder upwards. Right, so it is being winched up. They're bringing it up. Right, rather than lowering it to the surface, they're bringing it up. All right, but what if we reduce the tensions considerably? Instead of having a tension of about 3 million newtons, what if we only apply a tension of 10,000 newtons? Okay, 11,500 newtons to be precise. Okay, well, in the same sort of situation, we would literally just use the exact same expression we got from our sum of forces, but we just put in a different number for tension. Right, so instead of putting in this number, we'll put in this number, the 11,500. Okay, and what do we get? We actually get a negative value this time. And that means that this time it's accelerating downwards and rather rapidly. Okay, so the idea here is that this is nowhere near enough tension to support it, nor bring it back up. So all this tension is doing is slowing its descent slightly. Okay? All right, well there we have it. Cool. Okay, all right, moving on. Another question. So a certain object floats in the fluid, or in fluids of density 0.9, 1, and 1.1. So 3 different fluids that vary a little bit by 20%. All right, and then rank the buoyant force exerted on the floating object by each of the fluids, least to greatest. Think about this one. How would you approach it? Okay? Well, you actually don't have to at all, because it's a gimme, right? You just look and you say, floating means equilibrium. And in that case, the buoyant force has to be equal to the gravitational force. Really? And that means that in each case, the buoyant force is the gravitational force. It's the same object every case. So that means the buoyant force is the same. It's just always mg. Just the mass of the object times gravity. It's just the weight of the object. It doesn't matter. If it floats in all 3, then it floats. And if it floats, the buoyant force is its weight. Now, it wouldn't float at the same level. There'd be a different proportion of the object sticking above the water line or the fluid line in each case, but the actual magnitude of the buoyant force would be unchanged. All right? So let's think about that. How much of an object does stick above the surface when it floats? And let's consider ice. So ice has a density of 917 kilograms per cubic meter, a little bit less dense than water. Probably know about that whole idea that ice is less dense than water, right? And you certainly observed it in everyday life, all right? As compared to pure water with a density of 1,000, again, taking not salt water or anything, just pure water. What percentage of ice floats above the surface of water? Okay, right? So here's this is my attempt at an iceberg floating in the water, which maybe I should have used salt water, but regardless, right? Here's an iceberg-like thing, or it could be ice cube, but you can see the way I drew it. All right, so gravitational force, all right, and buoyant force. Although I mislabeled it it should be B here. Okay, water, positive Y up, right? There's the ice, and you can see already, I'm expecting to find a small value for the percentage that floats above the surface of the water, right? And you kind of know that. Maybe you've even heard that idea that 90% of icebergs are beneath the water. Well, look here, right? The density of the iceberg is 917. Density of water is 1,000. So if we think about it, then we should be able to find that it's just, the ratio after all, right? It's just the ratio of the densities. So right there, that should give us, 91.7% of the iceberg is beneath the waterline, okay? And that, so you could just say, oh, I'm done. But let's show it. Let's show where that comes from. Start with our sum of forces, equal to 0 because system's at rest, okay? Plug in the density, or plug in the definition of the buoyant force, replace mg with rho g v, okay? V displaced and V ice are not the same in this case, all right? So then we solve for the volume displaced, ratio of the densities times the volume of the ice, right? And this is the expression that I mentioned in the key formulas, all right? So here's where it comes from, right? You got your own little derivation, all right? And so then the volume above is the volume of the ice minus the volume displaced. And so percent above is then just going to be volume above over volume ice times 100, all right? And then we just replace the volume above with volume ice minus volume displaced. Volume displaced, we know, has this form here, which means the volume of the ice cancels out. So we end up with this lovely expression, and it's just going to be 1 minus 917 over 1,000. 917 density of ice, 1,000 density of water, and then change it to a percent. We just multiply by 100, and we get 8.3%. And that makes sense, right? Because that is just literally the difference between, that's just 90 or 100% minus 91.7%. Okay, and that was the whole idea, that 91.7% of the iceberg is below the waterline. But this is where it comes from. Okay? All right, so, that's, again, simple idea, and one you can kind of just cheat and say, oh, I know how that works. But here, this is really starting with Newton's second law and being confident that it works. Okay? All right, last one. So a raft is made of Sitka spruce with a density of 450 kilograms per cubic meter, has a width of 2.15 meters, a length of 1.88 meters, and a height of 18 centimeters. It's set afloat in fresh water with a density of 1,000 kilograms per cubic meter. If a person with a mass of 91.5 kilograms was to step onto this raft, how many centimeters of the raft would be above the waterline? Okay, all right, so how do we do this? So by the way, I looked up Sitka spruce because it's one of the least dense woods out there. So make a really good raft. So here's the idea, right? we're going to try to find the volume dry, because here, and then we'll change that over to centimeters. And then we have the volume displaced, which is also the volume wet in terms of the wet raft. And then our forces are the buoyant force of the raft, the gravitational force of the raft, and also the weight of the person. And the person isn't going to get wet, so they're not going to be displacing any water, right? They're just on top. Positive y is defined as upwards. All right. So here's our F net forces. Okay, equal to 0 because we're assuming that the boat floats, right? They're not going to sink, right? And we're not in danger of that. Indeed, we'll find it. Our assumption is correct. Definition of buoyant force: gravitational force with m rewritten as density times volume. All right, and then mass of the person times gravity because we're just given the mass of the person. We don't care about their volume or their density. Okay. Okay. And here I'm just pointing out that the volume of the raft divided by the volume, or the volume of the raft divided by the volume dry, is equal to the ratio of the height over the height dry. And that's because it's a rectangular solid. So the idea is that they have to be equal to each other, right? There's a direct linear relationship between the total volume of the raft and the total height. This is the total height, by the way, and the height dry and the volume dry. Okay. All right. And then the volume dry is just the volume of the raft minus the volume displaced. Okay. So then we're going to go ahead and go back to our sum of forces, and we'll use this in a minute. All right, and here I've just simplified things a bit. I've obviously canceled out G as shown up above. All right, and then we're going to solve for the volume displaced. Okay, and so then here's the actual volume of water displaced by the raft, 0.419 cubic meters. Okay, well, then let's compare. So then the height dry, because remember that's what we were asked for. We're asked for how much floats above the water line. Okay. Be above the water line. So the height dry, that's the height above the water line, would just be h, and then multiplied by this ratio, the volume of the raft minus the volume displaced divided by the volume of the raft. Okay, so then we have our 18 centimeters, the overall height of the raft, and that's this here. Okay, and then we have the volume of the raft, which I didn't show being solved for, but all I did here is I just multiply these numbers together, 2.15 times 1.88 times 0.18. Okay, and that gives me 0.72. Okay. And then minus the volume displaced that we found through our sum of forces and divided by 0.72. These would all be cubic meters, but the cubic meters all cancel out. Okay, that's why I didn't write them in. And so then we get a height of 0.076 centimeters. So 7.6 centimeters is dry. All right, so about half, right? About half of the raft is sunk beneath the water line, and another half is above the water line. Okay, kind of a good way for a raft to float. Seems about right. Okay. There wouldn't be too much sloshing over the side, maybe. Okay? All right. So now, let's look at part B. So our part B, all I'm going to do is rebuild the raft. It's going to be the same person, but I'm going to rebuild the raft with Brazilian rosewood. All right? Now, rosewood is one of the densest woods out there. Right? Again, I just looked up densities of woods. It's 900. It's twice as dense as Sitka spruce. Would it make a good raft? Okay, well, let's see. Okay? So we're going to compare the downward to upward force. So in this case, I'm just going to look at the maximum buoyant force, all right? And the maximum buoyant force would mean the raft is fully submerged. So this is the idea, because here we're asked, would they stay, dry? Well, there could be the case where they'd just barely be dry is if the raft sunk all the way down and was like touching the water but hadn't started to sink yet. All right, so I'm giving them the benefit of the doubt and saying, okay, that's the maximum buoyant force. The raft is fully submerged but not sinking. And so the maximum buoyant force in that case, fully submerged, is 7,130 newtons. All right, and here this is the total volume of the raft, this is the density of water, and that's gravity. Okay, and then let's do the gravitational force. Well, the gravitational force is going to be combined weights of the two things, so just gravity times mass of the raft plus mass of the person. All right, the mass of the raft is just going to be given by the density of this rosewood times the volume, and then the mass of the person is given as 91.5 kilograms. So let's check it out. We get 7,310 newtons. That means that they would definitely get wet, because look, the gravitational force is greater than the maximum buoyant force, which means that the raft would sink, they would get wet, and they would just continue sinking. They'd better jump off, because otherwise they're going to go down with it. Now, if they're less dense than water, and people who are less dense than water, depending on what they're wearing, then I guess they would contribute a little bit to the buoyant force, but not enough to stop the raft from sinking. And also they're not tied to the raft, hopefully. So the raft would just sink. Okay? And so here we have it. Gravitational force is greater than the buoyant force, so that means they sink, which means they get wet. Okay? All right, well, that is it for our introduction to the buoyant force. I hope seeing these simple force problems has been interesting and a good reminder of things we've done before, and a good kind of added force to our list of common forces that we know how to deal with. All right, well, thank you for watching. Bye.